Hello, we are Kim Detection. My name is Mary Doobie, and I am accompanied by
Caitlin Stewart.
Ines Kiera.
And Bethlehem Solomon.
We are advised by Dr. David Navant, and our client is Dr. Robert Bowie of DME. Today, we are going to be presenting to you the biohazardous multi-gas detector for firefighters.
So this presentation will include our motivation, which means understand what the issues are and what needs to be changed, the goal of our project and strategy. Then we'll go over our solution and the design of our device. We will talk about the design components and how we manage to work remotely on different parts of the device. We'll talk about the different testing performed and results. We will do a quick device performance evaluation. And finally, we will conclude with what the team would want to improve, add, or pursue for future work.
We were introduced to the problem of increased rates of cancer development among firefighters. The National Fire Protection Association, also known as the NFPA, states that 42% of firefighters are aged 30 to 49 and have been on active duty for 10 or more years. It is also being recognized that modern residential fires are beginning to have more in common with hazmat incidents rather than what used to be as legacy house fires. This is due to items in households being composed of mostly plastic or synthetic materials, and also more furniture in households being made with flame retardant material. There are approximately 84,000 chemicals being used commercially today that can be found in households and commercial buildings. Firefighters are being exposed to these chemicals during fires through lung exposure due to overhaul of synthetic and plastic residue when the fire is out and removing of their SCBA mask too soon, and also dermal exposure. And with skin absorption or dermal absorption, this is increased by 400% with every 5 degrees increase of a fire. The exposure to fire and chemical hazards of firefighters who have been on active duty for 10 or more years increases their rate of developing cancer by 29%. These common cancers that are being developed are multiple myeloma, lung cancer, skin cancer, and brain cancer. There's also the issue of the rise in fire protection costs. In the US, there are currently a total of 27,000 fire departments listed on the NFPA registry. 70% of those fire departments are run on volunteer base, and those 70% of personnel that are volunteers are required to pay for their own training, and this also often includes their own equipment. Here in Orono, the fire department has a total fiscal year budget of $11,000. This is not a lot when you think that this has to cover costs of gas for the emergency medical services vehicles and also the fire engine vehicles. It also covers costs of any equipment used when they are called to a fire scene. And you also have to take into consideration that most turnout gear can cost up to $3,000. So we are tasked with trying to build a device that will help these firefighters reduce their risk of developing cancers, but also not implement more of a cost for their protection.
Due to these problems that we previously talked about, we have identified the need for a device to address the mortality and morbidity rates of firefighters due to the exposure of biohazardous chemicals in a way that does no harm, such that it does not detrimentally affect their gear, and in a way that creates no interference to the user in that it doesn't stop them from being able to perform their job.
So to address the need statement, the fire station needs a device that is safe to use, detects chemicals, which we want it to be hydrogen sulfide, ammonia, and oxygen levels. It needs to be functional, so communicate via Bluetooth to the fire station or the fire truck, and have 3 forms of alerting the user of a detected gas, and also be marketable, which is inexpensive, affordable for the fire stations, and durable. So Our team has then designed the TUNAPE multi-gas detector, which is shaped this way for better grip when the firefighters are wearing gloves. This device meets the NFPA standard, which is the National Fire Protection Association standards, and is user-friendly. The concussion boost was designed to absorb any shock in case the device was dropped, and the qualitative danger levels for the gases detected are displayed on the screen. In order to notify the user of a detected gas, the TUNAPE also has three forms of alert: an alert system, it can vibrate, light up, and also has a sound system.
The TUNAPE consists of 5 main design components, the first of which being the exterior shell. The exterior shell was 3D printed using gray PLA. We printed 2 shells as possible options for the exterior, a thicker shell with a 30% infill and a solid build support as seen in the right-hand picture, and then a thinner shell with a 60% infill without any sort of build support. A 1 centimeter wide piece of rubber was adhered to the rim of the shells using super glue, with the intention of it acting as a shock absorber, as we have previously mentioned, as well as to protect the seam when the 2 shell halves are put together to form the complete exterior shell casing.
Next, we have our LCD screen. This screen is a 16:2 liquid crystal display, or LCD screen, and it is used as an interface to display the quantitative and qualitative data collected from the gas sensors. So on the right-hand picture, you can see that the top of the screen where it shows detected chemical, this is where the qualitative data would be shown, where it would say if the gas being detected was oxygen, ammonia, or hydrogen sulfide. In the bottom where the white boxes are, this is where our quantitative data would be shown, the percent by volume for oxygen, or the detected concentration in parts per million for ammonia and hydrogen sulfide. This LCD screen is connected to a MIDOC system, which is programmed through LabVIEW. The communication to the screen is incomplete without the use of an Arduino, so we took use of a simulation in Tinkercad to connect the Arduino to the LCD screen, which is what is being shown on the right.
One of the other major components of our device are the biohazardous gas sensors, which we focused basically on the oxygen sensor due to the limited amount of materials that we were able to work with this remote work system. We focused only on the oxygen sensor. As this diagram reveals how the oxygen sensor in general works, as the in being the oxygen comes in, and there's the process, and the out being a voltage that we measured. So the oxygen enters the sensor through the capillary, which acts to limit the oxygen, or in general, the gas flow through the sensor, and reacts to the electrode surface being reduced to the water. And this reaction requires proton, and these are generated at the other electrodes where the water is oxidized to form oxygen and protons. The proton travels across the solid polymer electrode membrane towards the sensing electrode, and then the oxygen formed leaves the sensor via the vent in the base of the sensor, which our team intended to remove that through the fan that we were going to have. There's a flow of electrons from the counter to the sensing electrode, and this current is amplified in the circuit, eventually providing a voltage that is measured. And this current generated in the sensor is proportional to the concentration of oxygen. This slide reveals the circuit diagram for the oxygen sensor, how it works in general with the input of positive 5 voltage, which creates a bias between the sensing and the reference of -600 millivolt to give the output of a voltage recording in general.
Then for the multicolor LED, we were thinking of multicolor LED light strip 12 volt RGB, which red would mean the user should exit the scene due to high level of detected gas. Green, the device has detected a level of chemicals, and blue would mean just neutral, that the device is on and ready. So since we only had one Raspberry Pi and couldn't each member have it. The goal for the LED strip was to be soldered and powered to a 9-volt battery. The LED required 12 volts, so we tried to set up 2 batteries in series to get 18 volts and then use the converter adjustable power to get to the 12 volts required. The issue was that we needed a multimeter and other equipment to evaluate the voltage required. But you can see here on the bottom pictures that the 9-volt battery was enough for the LED to light up, but only for this short length, and it would not be around the whole device like we wanted it. Otherwise, it would be too dim. Unfortunately, we did not have a Raspberry Pi or an Arduino to control them, so it was not possible to change to the 3 colors unless it was done manually. So we decided to do a simulation on Tinkercad that connects the LED strip to an Arduino. The LED are different than the one that we have. Those ones require 5 volts, so we decided to work with that, and we wrote a code for the LED to light up once the gas sensor detects the presence of gas. Then the next schematics on the top right was found on Adafruit, which used the same LED strip as we do, but it uses 3 motor controller, also called MOSFET, to drive each RGB channel and gives the ability to fade the strips. Then the next way of alerting the user was the vibration disc. We decided to power them with a 9-volt battery. So as you can see, the vibration disc were soldered with 1 on top, 2 in the middle, and the battery on the bottom. This is the positional layout that would allow for the best spread of the vibration in the device, assuming that the user would hold it in the middle with a finger on the top. The disc required 5 volts, but we noticed that the vibration was not strong enough and not fell through the 3D printed shell. So we decided to go with the 9-volt to go higher, and the vibration was strong enough and fell through the shell. We were then able to use Tinkercad simulation to code and connect the vibrating motor disc to an Arduino, which would go off when the gas detects the presence of gas. Then we will talk about the tests and results.
The first test that was performed was the drop test to validate the durability of the exterior shells versus a control. The drop test was performed by securing a shaving razor with the blades removed within the shells using black electrical tape. This would simulate how the electronics would be mounted in the shells in the fully assembled prototype. The razor was dropped by itself as the control. We did trials of 3 at 3 different heights: 30.5 centimeters, 91.4 centimeters, and 183 centimeters. The drop test was considered a failure if the shell was damaged, if the razor was broken, or if the razor became dislodged from the shell during the drop test. Here we can see the results of the drop test. We found that the thin shell was actually more durable than the thick shell, with a 100% passing rate even at the highest height of 183 centimeters, whereas the thick shell began to show failure at the second height due to damage to the build support when the thick shell was dropped.
Next, we have our screen brightness test. The purpose of this test was to validate that our screen would be visible in dark or low visibility environments, which firefighters often go into. The screen visibility was measured using an iPhone app, the Lux Light Meter Pro, and was measured using illuminance in units of luminous flux per unit area, or lux. The test was considered a failure if the screen had a lower lux value than 7, which is comparable to the average brightness of an emergency light or red exit sign. Here are the results from this test. On the right, you can see the arm, which is the legend for the graph. So the measurements that we did were from fingertip to wrist, fingertips to elbow, fingertips to shoulder, to make sure that we established all the measurement points that our future work retractable strap would ensure. So as the distance increased from the screen, the brightness of the screen decreased, as would be expected. So the closest distance, which would be the hand measurement, had the highest lumens around 17, and then it decreased to about 4 lux. So from 60 to 70, or the full arm span of a person, that is where our minimum lux range was for our screen.
In the oxygen sensor test, our purpose for this test was to detect the level of oxygen that's present in the surrounding environment. And obviously the test, like I mentioned earlier, it composes of a chemical reaction in the sensor that produces a current proportional to the amount of oxygen or the concentration of oxygen that's present in the environment. And the parameter analysis results would be a failure if the oxygen is not detected, meaning if there's no any voltage or current that's sent to the output data to be read by the Arduino and revealed on the screen. Any atmosphere with an oxygen level below 19.5% by volume is considered to be an oxygen deficient. With this, we have the following graph. This graph is a calibration curve generated by the manufacturing company of this sensor device. The x-axis is proportional to the applied oxygen or the amount of oxygen that's present in the environment, and the y values corresponds to the sensor response to this amount of oxygen. As you can see in this calibration curve, the graph is has a relatively positive correlation. So this linearity test reveals that when the oxygen amount in the environment increases, the response of the oxygen sensor also increases, meaning when the device is being exposed to surrounding environment with higher amount of oxygen, then the device's or the sensor's ability to test this oxygen amount would increase. And also when there is only limited amount of oxygen present in the surrounding area, there will be a small percentage of oxygen that's being detected, which shows a good test for the future work when we intend to test this thing.
From the results of these tests, we were able to evaluate the performance of our device using metrics that we developed with our client, with a low score equating to unsatisfactory and higher scores equating to satisfactory or above expectation. It was determined that the device met the following criteria: durable in cases of being dropped, inexpensive to produce, lightweight in that the final prototype would be under 3 pounds, have a screen that would be visible even in low visibility situations, capable of alerting the first responders via visuals, vibrations, and sounds, and meeting the NFPA standards. However, the device was incapable of detecting multiple gases. We were also unable to test whether the device was capable of being used multiple times, how long the battery would last, if the exterior shell was fire resistant, if the completed prototype would interfere with the firefighters' ability to perform their jobs, and if it was water resistant.
So our team was able to complete components of the multicast detector, the TuneApe device, as can be seen in the large red circle. As future work, we would like to have a guaranteed battery life of 24 hours, which is the common length of a shift for firefighters. We would like to accurately detect relevant concentrations of not only the oxygen gas, but also hydrogen sulfide and ammonia gas. And of course, we would like to complete the final assembly of all components coded with an Arduino and working together simultaneously. With this is our conclusion of our presentation. If there are any questions, we would love to answer.